All right. Hello, everyone. Welcome to the PC seminar. And today we have with us Jan Marcinkowski from University of Wrocław. And he'll be talking on constant factor approximation for capacitated K-median in FPT time. So thank you so much for joining us, Jan. Over to you now.
Thank you. Okay, so I actually don't have a joint title. I'm going to be talking about two papers. So this is the first one, and this is the second one. So there are two title slides. Okay, and the first half is going to be about the first one, and the second half is going to be about the second one. And the reason is that they are sort of on the same topic. And the second one, which was requested, let's say, doesn't really make sense without the first. All right, so let's start with the first one. Let me first say, so the first paper is written together with some people, and among them is Michał, who worked at the University of Warsaw. And Wrocław and Warsaw are not the same two cities. They are different cities, even though people often confuse them. So this is Wrocław, and this is Warsaw. So you can see the difference. And okay, I'm going to segue into this strange topic of our university reform, but bear with me. We will get to capacitated K-median. And by the way, if there are any questions or doubts, or someone doesn't understand or doesn't hear me or whatever, please interrupt. Okay, so university reform. There are 43 public universities in Poland, in 20 cities, and a lot of private universities, obviously. And there is roughly 500,000 students. And our higher education minister or universities minister decided to make a radical reform of all of that. And he decided that he will pick 10 universities and provide massive funding, and everything else will be closed down. Like complete revolution. And the question is obviously, how will the 10 universities be selected? And the answer is every university will declare how many students it would be able to teach. And then the state, the country, the minister picks the 10 universities that have total capacity of 500,000 students. And also these students don't need to travel. Like we want to minimize the travel, the total travel time from students' locations to the universities. So as we can see, this is a capacitated K-median problem, where we have facilities, which are these universities. We have clients, and these are the students. And there is a metric. Obviously, in our case, it's a metric of Poland, of our country. There is a capacity function. These are these declarations. How many students can a university teach? And there is number K, which in our case is 10. And what we are supposed to output is a subset of these facilities, these universities, which has exactly K elements, and every facility is serving at most as many clients as it is able to, and the total distance from the clients to their facilities is minimized. Is that somewhat clear? Can anyone confirm that it makes sense? No confirmation.
Yes, there are confirmations.
Yes. Okay. Yeah. Okay. Good. Okay. So we have our capacitated K-median problem, and we have a reason why we started working on that. So one can see that feasibility is very easy to check. We just take 10 biggest universities and see if these 10 universities are enough to serve 500,000 students. clearly the problem is NP-hard even without the capacities, because K-median, everyone knows K-median is NP-hard. Then there is, it's a fact that hadn't been described anywhere precisely, but it has been known that there is a log K, O of log K approximation algorithm that runs in polynomial time and for this problem, for this capacitated K-median problem. And I'm going to describe this algorithm in the next slides. And then there is a series of quite complicated papers on constant factor approximation, and which is not known per se, but it is known that you can do constant factor approximation if you violate either the capacities, which means that you make universities teach slightly more students that they are able to, or you violate the number of universities. You instead of opening 10, you open 1 plus epsilon times 10 times k. And finally, well, not finally, the problem is W too hard, even without the capacities. And our result is that you can do constant factor approximation in time fpt of k, which is a step into the direction of this constant factor approximation, let's say. All right, so what we will see next is the pink thing, which is the folklore log K approximation algorithm, and the yellow thing in the at the bottom, which is our constant factor approximation algorithm in FPT of K time. All right. Okay, before we see the pink thing, we need to see the main trick. And the main trick is called L-centered metric. And it works like that. You have your metric. Our metric, as we said, is Poland. You pick number L, which is at least K. And you compute an approximate solution to an uncapacitated L median. So we found some L universities on our map. And you know that this solution defines a Voronoi diagram on the metric. So because it's an uncapacitated problem, so every student goes to the closest university. And then our L-centered metric is an original metric on these L facilities, but everyone else, to go anywhere, needs to go to this center and possibly to another center, and then to go into the cell. So to go from one cell to another, you need to go through centers, but even to go within a cell, you need to go through the center. So it's a very simplified metric, right? And even and here in these cells, you have clients, but you also have facilities that are not one of these L facilities. You can actually think that these L facilities also live somewhere in these cells, in these apprentices here. And the theorem that we have, or lemma, is that if you have an alpha approximation algorithm for capacitated K-median on these L-centered metrics, which are way simpler than the regular metrics, and this L-centered metric is built using a beta approximation for uncapacitated K-median, then in total you have alpha times 3 plus 4 beta approximation for capacitated K-median on the original metric. So what it says is that you can lose some constant factor and try and be solving this problem on this L-centered metric instead of the original one. Okay, doesn't make sense? Anyone? All right, so let's now see the pink algorithm, the folklore Makes sense, Andreas says. Thank you, Andreas. So we take this k-centered matrix, and when we try to figure out the log k approximation algorithm, we don't really care about constants in this approximation. So we just pick L equal to K, which is simplest, right? And so we have this matrix, and then we have this upper layer and this lower layer. So on the upper layer, we run AFERT tree embedding. So we sample one tree out of this AFERT algorithm. And we know that the expected violation of the distance is log K, because the top layer had K elements. And now we can solve the problem, the capacitated K median on tree, exactly via simple dynamic programming. So that's basically entire log K approximation algorithm. All right. And now we can. So this was sort of an example of this L-centered metric trick that we can use. And now we can use this L-centered metric trick for our problem. So the way we do it is by asking ourselves, if we did select the facilities in the capacitated K median, can we in polynomial time find the cheapest assignment of clients to the facilities? So if anyone would like to guess. So the answer is yes, we can. And there are many ways to argue that we can, and probably the simplest way is to say that this linear program is totally unimodular, so it has integral solutions. Okay, so what we established here is that if someone told us which facilities to open, we could assign the clients to. We could, well, one can see that it is sort of a matching. We can match the clients to the facilities in polynomial time. Okay, so now let's think of this exact algorithm for uniform capacitated K median on a center metric. Uniform means that every university has the same capacity, which in reality is not true, but let's start with that. So what we can do, because we are now in FPT of K, we can guess in each cell of this L-centered metric how many facilities should be open. And once we have guessed that, it only makes sense to open the facilities that are closest to the center, since every facility has the same capacity. So we just guess the numbers and we open the closest facilities, and everyone, and then we do the connecting with this linear program. Okay, so this was quite simple, right? But in non-uniform, meaning every university having their own capacity, this greedy strategy here is might not be sensible, because it might make sense to open a facility that's further from the center, and but can serve more students, right? So we need some additional trick, and there is a second trick here. And the second trick is to divide every cell, each of these Voronoi cells in L-centered metric, into rings of geometrically growing distances. We could call them buckets. And then instead of guessing how many facilities should be open in each cell, we can guess more granularly how many should be open in each cell, in each ring or bucket. And there is, well, this number of possibilities. But once we have guessed that, we have only lost epsilon on these distances. But in each cell, now in each ring, it makes sense to open the facilities of highest capacity, basically. So we can again have a very simple greedy strategy in each ring. And that's basically the approximation algorithm, the almost exact algorithm for non-uniform capacitated K-median in L-centered metrics. And now we need to combine it with an old algorithm for uncapacitated K-median, which opens K times log n times 1 plus 1 over epsilon facilities, but gives almost exact solution. And the thing is that if you put here in place of L, if you put this number, then it's by a trick that probably most of you know better than me, this is still FPT of K. So we have this approximation ratio, which is 7 plus epsilon. Okay, so this was the first half, which went very fast. So probably someone should ask some question, because I'm sure it was too fast. All right, no one is saying anything. Okay, so this is our result from 2019, I think, maybe late 2018. And afterwards, we have been beaten. So Vincent Cohen Haddad and Jason Lee had this algorithm that is basically strictly stronger than ours. Theirs is quite complicated, and one advantage of ours in comparison with theirs is that if we really wanted to solve this university problem, then I think our time complexity still is feasible to compute, and there isn't probably. But obviously we are not trying to solve this university reform problem, right? And an additional result that they heard in the second paper in the same conference was that that this 1 plus 2 over epsilon factor cannot be beaten even for uncapacitated K-median in FPT of K time. And in fact, they also matched this with an approximation algorithm of the same ratio. So the state of the art now is that the best algorithm is 3 plus epsilon approximation, and there is this hardness of 1 plus 2 over E, and this 1 plus 2 over E is known for uncapacitated version. And it's one valid open question is to have stronger hardness result for the variant with capacities. And somehow we are not able to do that. All right, so this was the first half. This is everything I have on the first paper. So if anyone would like to ask something, go ahead. I really encourage you. And unless there is. All right, so let us go to the second half. The second half is in a slightly different set of with a slightly different set of authors. Okay, so let's go back to our university reform, because everything started with the university reform, and as we know, reforms, especially radical reforms, quickly tend to be parodies of themselves. So it turned out that instead of leaving 10 universities open, the ministry will just close 10 universities. So this way we have a slightly different problem, right? We have a problem where there are n universities, but we are asked to close L so that this sum of distances is minimized again. So which is again k-median problem. So from the regular algorithmic standpoint of view, this is exactly the same problem. But once you think about FPT, it's a bit different because your parameter is now the number of universities facilities you are supposed to close instead of the number of facilities you are supposed to open. All right. And you can again consider this problem with or without capacities. So our results are that without capacities, there is a sort of an approximation scheme, which is 1 plus epsilon approximation in FPT of L time. However, once you have these capacities, although I think only our reduction only has non-uniform capacities. I don't know if that matters. Anyway, once you have capacities, you cannot beat 1 plus 2 over E approximation in FPT of L time, assuming gap ETH. So I'm going to sketch the algorithm, and I think I have a slide on the hardness as well, but I am not as well prepared when it comes to hardness. All right, so let's think about the algorithm. Since no one is protesting, if someone would like to protest, it's also encouraged. All right, so let's think about a naive approach to this kind of an algorithm, right? We have this Voronoi diagram here, and we are supposed to close L facilities and reroute their clients, and our objective function is the total of distances from clients to the facilities, right? So the naive approach would be for every single facility to compute a marginal cost of closing it, which is cost of rerouting its clients to the closest neighbors, and then pick L facilities that are marginally cheapest to close. So this is the first idea we can have. And this idea obviously doesn't work. And the reason why it doesn't work is that we could, for instance, here we can you see my mouse, by the way? My pointer?
Yes.
Yeah, good. So we have, if we close this facility here, a lot of students would be directed to that one. But if we close that one as well, they don't have their backup, right? So all of your total cost is not the sum of your marginal costs. It's more complicated than that. So basically this approach doesn't work for that reason. So, all right. So the problem is that the facility that you may consider for supporting from the perspective of one facility may also be closed. So a simple answer to that problem would be to do color coding, to guess which facilities are considered for closing and which are not considered for closing, which are going to be supporters. And once when you compute these marginal costs, you would maybe only reroute students to the nearest supporter facility, not to the. So here, if you are redirecting students from here, you would redirect them to the green facilities and not to the red ones. The problem is that in the optimum solution, basically everyone who is not removed is a supporter. So there is a lot of supporters, right? And it is enumerating every such division into potential closers and supporters is the same as enumerating every solution, basically. So that's too big space for guessing. So we need to have a slightly more refined idea. And this more refined idea is that, imagine we have a solution S. S is the set of the facilities that we are closing. And then for a single facility in S, we can define epsilon supporters of this facility. And there are two types of epsilon supporters. So here F is this one, this city here. It's called Częstochowa, by the way. And one supporter is the city closest to F. And the other epsilon supporters are those that in the solution S, the cost of rerouting clients this piece. How to say that? So we have a solution S, and we know exactly when everyone goes, where every student is rerouted. So let's look at the students that were assigned to F before, and let's look at where they are rerouted. And we look at these neighboring facilities that take a lot of this rerouting cost. So every one that takes at least epsilon divided by 6L² of the total cost is an epsilon supporter. And we can see we can see, by the way, that every epsilon supporter is also a supporter. Epsilon supporter is never closed. All right. Yeah, one thing that I didn't say is that among these closest to F, we take the closest one that is not closed in the solution S. So now what we can do is we can guess the red set, the set A, which is a superset of the facilities that we are going to close, and the B, which are the green things, which is a superset of the things that are going to be epsilon supporters. And the important thing here is that there are not too many epsilon supporters, and that's basically a counting argument here. And the second thing is that basically what you can do once you have a solution, you can reroute everyone to epsilon supporters and pay little for that. So now the idea is that you do color coding with this partition into red things and green things, and then you reroute everyone to these epsilon supporters. And that's the second algorithm. And I'm not going to say more about this. There are obviously some triangle inequalities. There always need to be triangle inequalities when you talk about K-median, but that's basically it. And we have just spent half an hour. So any questions, people, please. All right, so the final thing is the hardness of approximation. I only have one slide on that. So the hardness of approximation is basically for the capacitated co-L median, is basically a reduction from maximum K coverage, because a similar result has been known for maximum K coverage. And And how we do it is we take the maximum K coverage, which is a universum and n sets. And for every, so we need to construct two things. One thing is, three things actually. One is facilities, the second is clients, and the third is distances between facilities and clients. Okay, so facilities first. For every set in the maximum K coverage, we put as one facility, and this facility will have a capacity of the size of this set. Then for every element in the universum, you also have one facility, and it has a capacity of universum plus 2 for some reason. And then clients. So for every set, you have as many clients as there are members of this set. As there are members of this set. And for every client, you have as many, what I'm saying, for every element in the universe, you have universum size plus 1 clients. So you can see that in total there are how many things? Probably size of universe plus size of plus n facilities, and the total size of all sets plus universum squared plus universum size clients. And then the final thing we need to define are distances. So we see that there are quite a lot of combinations, right? There are 2 types of clients and 4 types of facilities. And 2 types of clients and 2 types of facilities, but the combinations can be more complicated because every client is connected to facility corresponding to set he belongs to and corresponding to set he doesn't belong to. And also every client originating in set is connected to facility originating in the same set and in a different set. So here we have distances. And on the right side, we have the definition definition, let's say, of these distances between clients originating in element and these facilities. And now I think the argument is that first, so imagine we computed a capacitated co-L median. And what is L? Or L is K. So now imagine we computed capacitated L median. And I think first thing to notice is that we cannot close any element originating facility. Is anyone following? A single person. Okay, no one is following anymore.
Can you just repeat the last few things?
Sure. So now we need to argue that this reduction is sane, right? We have these transformations and we have these distances, and now we need to argue that this all makes sense. So imagine we computed a solution for an approximate solution for capacitated co-L median on this instance that we built here. And the first argument is that this solution, whatever happens, cannot close any of these FL of U. Yes. And the reason is that basically it would be an infeasible solution because the total capacity would be smaller than the number of clients. So it's something that I guess can be verified. So even someone who is good at multiplying probably should be able to. And now, so now we know that this solution, this approximate solution that we computed, only closed these F set facilities, and it closed K of them. So now what we need to do is argue that these K sets are a good approximation for maximum K coverage. And I won't present an argument for that, but basically that's the idea. So yeah, it took surprisingly little time, everything, but and that's the picture I don't have copyright for. So if anyone would like me to go back to any moment or ask a question, maybe it would make sense.
So any questions or comments?
Comments are good as well, yeah. If someone would say where they were lost.
Hi, can I just ask a question?
Absolutely.
So if you go back before you talked about the hardness, you talked about these algorithms. And so this is because you had two algorithms somehow, right? You have for capacitated and uncapacitated somehow.
Yeah,
right?
sorry. You mean the second paper?
Yeah.
The second paper? No, one algorithm.
Oh, there was.
Oh,
one.
yes. I went way too quickly. So we have. We have one.
The second one was. Oh, sorry. Okay, the second one was the lower bound for the capacitated. Yeah, got it. Okay.
And the algorithm, it's some guessing and then basically greedy.
Right. So, I mean, you didn't really say how this, where does the 1 plus epsilon, okay, let me ask a very concrete question. Why do you need this L squared there to get a 1 plus epsilon approximation?
Why do I need L squared? Okay, so one reason is you need the number of these epsilon supporters, the total number, to be small, so you can guess their supersets. You can sparsely separate them from. So that's one thing, and the other thing is that you don't want too large bound here, because the further away you are, the more support, the fewer supporters you have.
Yeah.
So this number works.
So the L square is sort of to control the running time, essentially. Yeah, at the end.
Yes.
Epsilon controls the cost. Yeah, somehow.
Yes.
Okay. All right. Yeah. Thanks.
Anyone else?
So what's the next open problem to study here?
There, I don't know. Maybe Michał knows, but I have no idea, to be honest. No, I think that, for me, anything with these capacities is very, very interesting. But obviously, I have no idea how to construct any. It seems to be very hard somehow. And when it comes to approximating capacitated K-median in polynomial time, it seems that we are sort of stuck with LP formulations, and all of these complicated papers that were appearing, they use these very complicated LPs with and rounding methods and.
Okay, do we have any more questions or comments? Okay, I guess not.
I thought the university reform is going to hit some emotions.
Okay, so I guess we can conclude then. So, all right. Thank you so much, Ian, for the talk. It was really nice to have you. And thanks to the audience for being around. And we conclude our session today here, and see you all next week. Thank you. Bye.
Thanks.
You have some comments?
Good, thank you.
Yeah.
Stop sharing. Click.
All right.